work is it's a collaborative work, and hopefully I think my cursor. Okay, good. So then this can be recorded. So I have a lot of students over the years, and this program actually started from the NSF. This is called a MateriAlZ World Network, and that's pretty early on. They stopped the program, so I established the collaborations and have a lot of students join this program. So now I think Jiaming Zhu is now working at the Shandong University. Somehow I lost my cursor. Okay, so. And then Tianlong is a postdoc at City University with Xiti Liu, and Qianglong Deng, and was my group, and now it's become postdoc professor at Xi'an Jiaotong University. Yipeng is also my postdoc, my PhD student and postdoc, now back in Jilin University. And then Mike Mills is my colleague, now is my boss, the department chair at Ohio State, and working on electron microscopy. All right, so we start to work with the NASA program to create concentration modulation to tailor the strain avalanche, and then gradually migrate to DOE. And then we try to use radiation to create amorphous layers, and then try to create a mixture of the two phases, amorphous and crystalline, and then try to make the modulated structure materials this way. So let's start with these two animations. And so the first one, so I have a piece of metal, and then I create a notch here and the bottom, and then you start to load. So this is from Abraham a long time ago before he passed away. And this is large scale MD simulation. Oh, if I can get my cursor in here. And you can see this is from the notch when you apply load. So you induce a plume of dislocations. And this is all because of this long-range elastic interaction. They trigger this strain avalanche. And so this is about shear deformation by dislocations. And I would like to say this is probably the best roller coaster you can build. And this is much better than the human being can build. So the second example, this is from R.D. Jim's work. And this is about the martensitic transformation. This is also shear deformation. And in this one, I would say this is the best design of a piece of art. This is the patterns. It looks really beautiful. This is polarized light. You can see the martensitic transformations always start from this corner, and then they just went through like a domino effect. So if you look at those two, one real experiments, one animation, and if you look at those two different processes, you ask yourself, so all those plastic deformation or shear deformation in particular carried by either dislocations, martensitic transformations, or deformation twinning, or shear bending in metallic glass, they share a common feature. So that's the long-range elastic interaction, which lead to strain avalanche. So that's the common feature we have here. And so long-range interaction as is autocatalysis, which gave you the strain avalanche. So if you look at the stress strain curve, you can see that you have this initial elastic region, and then all of a sudden you get this plateau for the strain avalanche, the burst of the strain. That's the same thing for martensitic transformation. So you have this elastic region which load, and then after you reach a certain critical stress, the transformation start. So this is a stress strain, and if you use a temperature strain, I have the same hysteresis loop. Then you're going to have this the plateau at the strain avalanche, and then the strain avalanche, and then you can reach into martensite, and then you can elastically form the martensite again. So those kind of hysteresis loop, stress strain hysteresis, it's good for certain applications, damping, and then some others joining. But for the other applications, those may not be the ideal stress strain curve you want. So the key is, how could we tailor the microstructure to control the strain? Because those ones, the strain avalanche, is very difficult to control. So if I don't have a different stress strain behavior, I can give you some motivations, the need for those, and how how we're going to tailor the microstructure of the material and try to control the strain release. If I want the strain release, let them release a little bit. And if I don't, and then I stop. So that's basically the idea behind this talk. So let's just talk about two things. The first one, how to regulate the martensitic transformation for controlled strain release, doing both superelastic and plastic deformation. The second one, how to regulate dislocation activities for controlled strain release. So those are two different topics. I'm going to skip this how to control or regulate shear bending in metallic glasses. So I'm going to start with soft confinement. So the whole theme of this talk is going to create compositionally modulated material in a bulk form, and then try to control the strain release. Related to that, as it's also structure modulation in the materials to control the strain release. So the first one I can talk about is I call the soft confinement by concentration modulation at the nanometer scale to micrometer scale to control the strain release. I can show you how. Second one is by what we call the hard confinement. So you have something transforming or deforming something they don't. Very different the strengths, or it's very different. This one is transforming materials, the other one cannot transform. Then they impose a hard geometrical confinement, and that's going to control the strain release process. And then there is the intrinsic coupling between the deformation twinning and the martensitic transformation. So this is going to allow you to create a structure modulation. You have a high density of twins. Then each of the twin boundary is going to host martensitic embryos. Then when you apply a load, the martensite is ready to go, but it cannot go too far because the confinement of the other twin boundaries. So this is, so all those techniques, which allow you to control the martensitic transformation, and then you can control the strain release, and then you can actually get very interesting properties. So here, I can emphasize on you can have linear superelasticity, ultra low elastic modulus. You can have this invar-Alema anomalies, which means that the thermal expansion coefficient is 0, or the elastic constant doesn't change as a function of temperature. We call it this Alema effect. And so then you can also have a progressive trip effect, and which give you excellent combination of strength and ductility, so which give you work hardening and then prolonged uniform elongation. And then for dislocation activity, it's a similar story. We can create a spatially modulated precipitated microstructure. I have coarse and fine and so on and so forth. In this case, you can confine the activity of dislocations, and then you can also have a good combination of strength and ductility. All right, so that's basically the story I want to tell you today. So the motivation for this first topic to control the strain release during martensitic transformation is from this idea of bioimplant. We know titanium alloy is very good structural materials, but it's also good structural materials in human body. So basically, that's the bones in human body. I call those ones structural materials in human body, and it's biocompatible and light and chemically stable. So that's the implant, and then this is what we call the second generation. That's all the titanium alloys, kneecaps and hip joint, and then so on and so forth. And but if you look at the actual environment, so for the requirements for the modulus, so the human bone modulus is around 20 gigapascal. And if you look at the first generation stainless steel, titanium alloy, second generation, it's all way higher than the 20 gigapascal. So that's the human bone is around here. So that's what we want. And so basically, the ideal implant material is going to be 20 gigapascal modulus plus 1 gigapascal strength. We want to have the models very, very resistant. You don't want to have metal debris get into your bloodstream, and that's going to causing a big problem. If you know the Frank theory about ideal strengths of materials, right? So usually the materials yield at 1/100th of 1% or even lower of their ideal strength. And the ideal strength is about 1/10 of this shear modulus. So if you want to have 20 gigapascal modulus, 1 gigapascal strength, you want the materials to yield at 50% of their ideal strength, not 1%. So theoretically, you just can't do it. So we have to use some trick to realize that. So you have to rely on structure transformations. You want to utilize this so-called pseudo modulus, the pseudo elasticity. So this is the true elasticity, and then this is the pseudo elastic, and then you can return to the original. This is elastic, but this is pseudo elastic because you have the phase transformation there. So the goal here is, if we can control this strain avalanche here, turn this stress strain curve into this one, we can really realize 2 gigapascal, that's the 20 gigapascal modulus and 1 gigapascal strength. So that's the idea behind this approach. All right, the idea is pretty simple. So if we take this titanium alloys, this is biocompatible. This is the chemical composition, and that's the short terms. This is Ti 2448. If you look at the MS temperature as a function of niobium content, you can see very strong dependence of MS temperature on niobium content. And then the critical stress to trigger the Martin-Celic transformation for stress-induced Martin-Celic transformation, it's the same story. It heavily depends on the niobium concentration. So the idea is, if you can create a concentration modulation in your materials in bulk forms, locally you can have some materials which are going to have the Martensite is already stable at this temperature. And then the others is gradually change the stability. And then for some of the materials, you had to go to very low temperature in order to transform into Martensite. Very difficult to transform. The same thing for the applied stress. So the idea is, if I can design a compositionally modulated materials, you have niobium lean, niobium rich. They form this onion ring-like microstructure. Then when you apply a load or when you lower the temperature, you see here the niobium lean region. So I have the transformation occur at a pretty high temperature or at very low stress. And then this niobium lean regions, the pointer down. So this lean region, they cannot go too far because it is surrounded by the next layer, and which has a different transformation temperature or stress. Then when you need to lower the temperature or you need to apply a little bit higher stress, then you can have this layer transform. And then this layer again confined by the next layer, and so on and so forth. So in this case, the transformation is going to go from this one, and then you're going to go to this one. So you're going to transform a little bit at a time while you increase the stress a little bit of time. So that's the hypothesis. And we can design those microstructures. And then for this particular system, they have a spinodal decomposition in the system, which create this nanoscale concentration modulation, niobium lean and then niobium rich. And then that's going to be host a certain Martin-Celic embryos. And then when you apply load bigger, they're going to grow. So we try to test this hypothesis first using computer simulation. So we have two systems, uniform system on the left, and then we have this modulated systems on the right. So this is the concentration field, the uniform concentration. And now we have, this is a modulated concentration. And then now we say, okay, when you apply load, we see how the microstructure change. And so in the uniform system, and then you have this one transform into Martensite, and then when you unload, then this become 100% of austenite again. So this is a structure order parameter to show you this is transparent. That's 100% of austenite. And in this case, because the concentration modulation, and then those regions niobium lean, then you have Martensite which is stable. After first cycle, those ones are going to come out, and then those become stable. It doesn't disappear anymore. And then when you apply the second,
we have to reshare the slide.
Oh, okay, sure.
I guess now it's
Oh, that's good. Okay, so now when you apply a load, again, those ones are ready to go. And then, so if you look at the stressing curve, this is for the uniform system. You have this big square-like hysteresis loop. And then if you have this one, so this is small plateau is to induce the formation of those stable embryos of martensite for the first cycle. After the first cycle, the second cycles, you just become completely linear superelastic. And then the elastic modulus is much lower compared to this one. And then for this one, this is a combination of elastic and then pseudoelastic modulus. And then we can track the microstructure change. By the way, this is done by the phase space simulation. You track this is the first cycle upon loading. And then this is unloading. And then the same thing, the second cycle, you already have a stable martensite. Then it's loading. And then, so in this case, and then you can see, okay, that's after this is upon loading, and then you take this microstructure back to here, and you do unloading, you return exactly to this microstructure that's similar to this one. So if you look at the stress strain curve, that's the first stress strain curve, second, third ones, you put on top of each other. The third one just is basically become on top of the second one. It's stabilized very quickly. Then you have this is a linear superelastic behavior. All right, so then, of course, this is theory and modeling is obviously as a hypothesis if you don't have experimental evidence. And so this is the for this particular alloy, this is atom probe data, shows you do have the modulation of niobium content, and this is titanium content in the alloys. And this is the stress strain behavior from 400K all the way down to 4K. And you can see this linear superelastic within a very large temperature range. So this is make this materials become very, very attractive for this bio-implant applications and for some other applications as well. So encouraged by this success, and we say, okay, shape memory alloy is nickel type. That's the one we use traditionally and then in the stand and other biomaterials. And then we say, okay, could we try this materials, make the modulus as low as the one as about the 20 gigapascal? So we say, okay, that's the good news is the dependence of the MS temperature or the critical stress for martensite transformation on the nickel content is just like the one, the dependence of the previous nickel, the titanium alloys on the niobium content. You have a very steep dependence on this nickel content. We say, okay, let's design a spatially compositionally modulated material. So we say, okay, let's say we have a layer. This is the top layer is about 70 nanometers. This is highly nickel rich. And then this is going to stay as austenite. And then we have this about 70 nanometers in the bottom. That's nickel lean. That's basically you can have a martensite. And then this is transition layers. You need to apply stress to transform those material gradually from austenite into martensite. So that's the concentration gradient that we designed, we optimized, and then we say, okay, if you have this concentration gradient, this is how the different parameters, MS temperature, sigma MS, this is stress to induce martensite transformation, the eigenstrain values, how they change as function of nickel content, and then that's the hysteresis. And upon loading, unloading, you can see this is almost like linear superelastic, and then you can have, this is the modulus, the apparent modulus is only 8.4 gigapascal. And then you can have the 4.6 work output. That's the strain. All right. So that's the microstructure evolution process. And so this is the first cycle upon loading, unloading, and then the second cycle. And then, but this is just so good only on paper. If there's no experimental evidence, this is still a hypothesis. And we thought we're going to try to find experimental collaborators and then try to do this film growth. And we talked to a few groups, and somehow it's been taking very long, and we didn't produce much of the result. It's okay, let's just go ahead, publish this paper. And then hopefully when the people in the experimental community, when they read the result, they may get excited, and then they may try to do it. But so far, I haven't seen any of the experimental result yet. And we just realized that probably you are modelers, theoreticians, and you can just do whatever you want. And then you can design this materials, but it's very hard to do in the experiment. That could be true. And then we say, okay, let's try to do something different. So we just need this concentration modulation. If by film deposition within such a small space, you want to create such a concentration gradient, that may not be easy to do in the experiment. Let's say, okay, if we can produce bulk materials, use the traditional trick of physical metallurgy, heat and beat, right? Try to produce something. It's okay. Let's try. So the modulus we can really, for those two different materials, the compositionally modulated materials, you can really get the modulus, apparent modulus, down to the human Wang level. So this is a very promising bio implant. So how can we create the concentration modulation that can be realized easily in the experiment? And we can find the collaborator which can do it. We say, okay, if you have a slightly nickel rich in the system, you can create a nano precipitate. It's called NFLTI3 precipitate. And so this is the microstructure of the precipitate that is simulated from the phase field simulation. But those precipitates, they don't transform from austenite into martensite because they are not austenite. So those ones are dead materials which cannot respond to the applied load. We say, okay, what we could do, we can simply heat it up, let the materials structurally transform back to austenite, because structural transformation is much faster than atomic diffusion. Then you take much longer time for the solute to partition into getting homogenized in the matrix. So by doing so, you can create a compositionally modulated microstructure, 100% austenite. Every single one can transform into martensite, but you have a modulation of the nickel content in this particular case. It's very similar to the niobium ones we showed before. So now we are doing simulation to see how the stress strain behave and then try to optimize in the computer again and try to reproduce what we did for the thin film ones. And hopefully this one can get some experimental collaborators and try to do the experiment. If nobody nobody can help us to do, we're gonna do ourselves and try it, because this is very easy to do. You have the nano precipitate, you heat it up, and then you try to dissolve. Okay, actually, to convince you this method is going to work, this is from Chris Hutchinson's group, Monash, and they take this. This is what called perlite in steel. If you know physical metallurgy, then that's the things you see. This is cementite and ferrite. This is lamellar, alternating lamellar structures. And what they did is, this is manganese steel. And then when you do up quench, you can dissolve carbon very quickly because the carbon is interstitial diffusion very fast, but manganese is the interstitial one, the substational ones. They don't diffuse that fast. They can control the time and temperature. You're gonna have a modulation of the manganese content in the system. And we know manganese is very effective austenite stabilizer. The modulation of the manganese is going to give you the modulation of the MS temperature of sigma MS. And then you're going to have this, when they do this the cooling again after up quench, they form this alternating layer of austenite, martensite, austenite, martensite. And then when you apply a load, the martensite simply grow and eat up the austenite, which give you very extended work hardening, or this trip effect, transformation-induced plasticity effect. All right, so that's very good. So now we say, okay, the key is just to create compositionally modulated materials in the bulk form. And we say, okay, additive manufacturing is so popular those days. And then this method allows you to produce, to make and shape and heat treat alloy at the same time. And then they have certain features that we can utilize, because this is ideal to create compositionally modulated material. So for titanium alloys, and usually for the workhorse TESX4, usually you have very little work hardening and it's very high strength, and then the ductility is limited. If you have this trip titanium alloys, this is stress-induced martensitic transformation, then you can create a very big this trip effect, but strength is low. So our goal is to use this composition modulation and try to create a materials, titanium alloys, which can allow us to push the strengths higher and also have decent amount of work hardening and uniform elongation. So that's the goal. So if you look at the additive manufacturing, if you use just one type of alloy powders, you're going to create chemically homogeneous melt pool. But if you use two different types of alloy powders, right? So this is stainless steel versus Ti-64. Here, it contains a lot of beta stabilizers, nickel, iron, and others. So this is just show you the EDS map of the how the iron content distributed in the individual melt pools, multi-layers. You see how they have this spatially concentration modulation for the iron content in this laser power bed build. This is material. So then upon cooling, and then you can see structurally, you have very fine scale dual phase. One is the alpha prime martensite in those regions. And then in those regions, you have the metastable beta phase. And then the beta phase is not uniform either. It's a metastable beta. You have a gradient of the metastability. You're going to transform into martensite at a different stress level. That's the same, back to the same idea I presented for the shape memory alloys. And then, so the reason why you have this concentration modulation is because when you form the melt pool, you can have different alloy powders. They have different composition. Mechanical mixing can only mix so much. In order to fully homogenize it, you need chemical mixing. You need atomic diffusion in the liquid state. But the lifetime of the melt pool is not long enough. You cannot create a homogeneous, you don't have time to homogenize the melt pool. That's you leave this concentration modulated material. And then if you look at how the deformation behavior, so you have dual phase, the red one, that's the metastable beta, and then the green ones, that's the martensite. So when you apply a load after strain, so you see this beta can transform into martensite. So that's the structure of the martensite, and that's the metastable beta phase. So in this case, by making the concentration modulation in space, you can create a very fine scale dual phase microstructure. And because the metastability of the beta phase, which can continuously transform martensite during deformation, which give you a strong trip effect, which offers the increase of the work hardening and uniform elongation. So you're going to have the fine scale of the dual phase microstructure give you the strength. That's the key for the high strength, even higher than the Ti-64. And then the trip effect give you the uniform elongation. So if you compare the properties of this we call the micro CM alloys with all the other Ti-64, and you can see this is the combination of uniform elongation versus tensile strength. It's much higher, and you say, okay, you are not a Ti-64. It's not fair comparison. You can compare with all the different classes of titanium alloys. It's on the figure on the right. This is all different titanium alloys, and then you can see that's also the combination of uniform elongation, tensile strength is still very, very high compared to the other alloys. All right, so that's the first story. And the second story I want to tell you, you actually can use the hard confinement as well. So you don't have to just do the concentration modulation. You can utilize nanoscale precipitate. So this is the one I mentioned, NFLTI3. In this nickel-rich shape memory alloys, you can create those nano precipitate. And so this is the NFLTI3. You can control the aging time and then the aging temperature and also the aging stress. You can create different size and different spatial distribution of this precipitate microstructure. And then experimentally, people have seen that for this precipitate, you can induce the R-phase martensite, which is coated the precipitate. So that's the embryos of martensite is ready and ready to go. When you apply a load, those martensite are going to grow. So that's basically that's the experimental evidence. We did the simulation, have the NFLTI3, and then when they grow, you create concentration modulation in the matrix space. You create concentration modulation already, because it's coherent precipitate, you have coherent stress. Both of them, the mechanical effect, chemical effect, is going to change the martensitic transformation behavior. So now, because of this layers of the depletion layers, then you're going to have the martensitic transformation much easier. That's how you create this coated martensitic layer around the particles when you apply load, and those ones are going to grow, and then you change how this volume fraction change as function of cooling as a temperature. And then if you see the experiment, we do see this the layer of martensite coat the precipitate. And then we say, okay, let's try to do more simulation exercise and then try to see if I age the materials at a different temperature, different time, I can create different, the NFLTI3, the precipitate microstructures. And I can try to optimize the microstructure for my stress strain behavior for the martensitic transformation. So we say, okay, let's take two different microstructures. And I quickly realized that if you have too few of the precipitate, it's too small as compared to the martensitic domain structures. Simply, they don't care too much about the precipitate. They just go like a regular martensitic transformation, and then you have this is a strain avalanche autocatalysis. You form self-accommodating microstructure. But if you have the right scale of the precipitate, you can partition the space into very small space. Then it's become harder to build the self-accommodating martensite. You had to build a much finer martensitic structure in order to have them to transform. And compared to this, you have a very fine scale of the twin structure of the martensite. Then you can change the stress strain behavior from this very big square hysteresis loop into this is very narrow and almost like the linear behavior. So that's the other story. And then, of course, after optimization, we see, okay, this is probably the best heat treatment for the precipitate microstructure. We can have no hysteresis, linear response of the volume fraction transform of martensite as function of the temperature. It's the same thing if you do the applied stress for the transformation. And now we have been talking to our experimental colleague, and then we say, hey, we already created this one in the computer. We have all the details of the heat treatment and to get the microstructure. Could you do the experiment? And now I think they agreed to do the experiment. So we are waiting for the experiment. So this one is the last topic for the spatial modulation. And so this one is a very interesting coupling crystallographically between the martensitic transformation and deformation twins. So this is really interesting. And I just want to remind you, if you have a dislocation in the ordered phase, for example, the Ni3Al, so that's the 1-1 atomic planes. You have different type of atoms, nickel and aluminum. And then this is the original. If you have just a disordered phase FCC, that's the translation vector. And then now, because of the different chemical species, because the order structure, the translation vector doubled. So this is a half 110. Now you need a 110 to have a complete repeat of the crystal structure. Then the dislocation core, in this case, you're going to split into, so this is Shockley partials, another Shockley partials, and in between, you're going to have the antiphase domain boundary, and then you have the Shockley partial and another Shockley partial. In between those ones, you have this is called complex stacking fault. So this is the core structure of this dislocation. We call it super dislocation in ordered structure. So if you have this introduction to physical metallurgy of dislocations, this is something you learn from those courses, right? So then this is called the fourfold core structure, APB, and then APB plus this stacking fault, intrinsic stacking fault, we call this complex stacking fault. So you have those kind of structures. So if you look at the energy landscape, so this is called a generalized stacking fault energy. So if you shear the crystal, how the energy landscape look like, and then this is show you the minimum energy pathway. You go along this valleys on the energy surface, and this is how you travel for the displacement, which gave you this core structure, complex stacking fault, antiphase domain boundaries, and then another complex stacking fault back to the perfect crystal. So you have this extended core structure. That's what you have. So whenever you have this energy landscape, across the core, you're going to see this CSF and then antiphase domain boundaries and another complex stacking fault, and then the peaks in between of them. So if you look at martensitic transformation in nickel tie, the regular shape memory alloys. It's very interesting. So here is the 3 different structures: austenite, B2, and then one type of martensite orthorhombic, and then B19, that's the B19 prime, that's the monoclinic. Let's just focus on the B19 prime. That's the common martensitic structure in shape memory alloys. If you look along this 011 direction, right, you draw this B2 structure, but you just take the nickel atoms out, only draw the titanium atoms. And then you're looking at this 011 direction, that's the 011 plane. And then this is how they look like, how the rectangles. And then if you say, I draw this parallelogram to guide your eyes for the transmission process. So if you shear this crystal by, so this part down, this one up, if you do the shear this way, then you're going to transform this one into this one. This is called the B19 prime. All right. So the B19, B2 to B19 prime, that's usually the group subgroup relationship for the structural transformation. Usually they don't go to anywhere else. You go from B2 to B19 prime, the B19 prime has to return to B2 on the way back for the transformation because the crystal structure, crystal symmetry. But if you look at this energy landscape, so if I take this B19 prime, if I continue to shear in exactly the same direction, allow the applied load to do work, then you're going to see this rectangles, this parallelogram become this rectangle. This is a high symmetry phase. It's called a base center orthorhombic phase. Actually, if you do DFT calculation, this one is the ground state. It's more stable than the B19 prime. B19 prime is stable at room temperature. So this has become really interesting. So this is a kind of a settle point along this energy pathway. By doing so, you allow this continue to deform, and then you jump onto, if you further deform, you jump onto another B19 prime. But this B19 prime is not the daughter of this B2, the initial B2. This one is from, belong to a new family. It belongs to a new B2. This B2 new and its initial, they are differed by a rotation, then by a twin relationship. Then you can continue allow the applied stress to do the work, and then you can deform this one further, you get this one, it's become this B2. But this B2, they have a twin relationship. And this B19 prime and this B19 prime have a twin relationship. Now we can think this energy landscape is just like what I had before. So if you have this energy landscape, right, go from here and then you go through those ones, like this energy landscape, then your core has to be extended. So now we introduce a new concept, extended twin boundary. And this has become very significant. So I just skip this one because originally you confine into one B2 family because the crystallography, because this is BCO structure, you build a bridge, you can go to infinite network, you can transform. And then in between those, the bridge, so this is a twin structure in martensite, twin structure in, so the twin structure in austenite, sorry, twin structure in martensite, twin structure in the martensite. Okay, so we did MD simulation, and so then you can say if you create these twin boundaries in austenite, and then if you relax it, the B19 prime automatically appear. So this say if you create a high density of twins, it's very easy to do. We do code rolling of the B2 austenite, you create a high density of twins. Then we start to characterize, we find within the twin boundaries, you can have embryos of the B19 prime martensite. So this high resolution show you we do have these embryos of martensite decorating the deformation twin boundary in B2 structure. So those ones you can say, I have high density twin boundaries which harbor the embryo of martensite already. So now when you apply load, they are ready to go. They transform into martensite. They grow and then consume the matrix B2 into martensite. But they cannot go too far. They cannot form self-accommodated. This is a big martensitic domain structure because the confinement of the neighboring twin boundaries. All right, so, and then if you do the mechanical properties, and then you can see this is a linear superelastic. It's very easy to stabilize. And then this is, say, the first cycle, second, and then the 30 cycles, you have very stable linear superelastic. Usually, strip memory alloys, you have to stabilize 1,000 cycles. It's called the training process. And then even for this linear superelastic, you can get 4% of work output. That's the recoverable strain. And the elastic modulus is also pretty low. All right. So this is to create a structure modulated materials to control the strain release for the Martin side. All right, I've got another 5 minutes or so. Okay, so now we say, okay, this is all about confine the Martin-Cedic transformation. Shear deformation of the same nature. Long-range elastic interaction, autocatalysis, strain avalanche. You can do the same thing for dislocation. So for dislocation, people have tried. So this is not a new idea. People have tried to create all different kind of gradient materials, in particular the green structures. And so there's a recent Nature review talking about the different kind of gradient microstructures, and then how you're going to increase simultaneously the strength and ductility. And most of the method they show is small scale lab, and then most of them using surface technology. It's difficult to create bulk materials with those gradient in green structure or precipitate microstructure. So what we try to do is, can we utilize what we learned of this concentration modulated material to create a modulation in terms of precipitate microstructure, and then try to confine dislocations. So back to the same idea, if you look at phase transformation for precipitation hardened materials, most of the structural materials for high temperature applications are precipitation hardened. So we have for this example, I have alpha phase and beta phase. All right, that's the free energy curve. Depending on where the alloy composition is, you can have different mechanisms. So suppose this is titanium alloy. My high temperature parent phase is the beta phase, BCC. Low temperature is going to be alpha, HCP. So now I have my alloy composition is within this red region. Then I can have my parent phase as a higher free energy. I can simply change the structure from BCC to HCP without changing the composition. That's called a congruent transformation. I can reduce my free energy dramatically without atomic diffusion. It's a very fast process, which can also give me very fine microstructure, very high driving force without atomic diffusion. When you move to the other side of this critical composition called the C naught, then within this range, even though you are not in the red region, you are in the green region, but you are so close to this point. Any composition fluctuation which allow you to go beyond this point, and then you're going to involve these congruent mechanisms. You're going to get also very fine microstructure. This is called pseudo-spinodal mechanisms. So the first one is going to allow you to create this very fine microstructure. The second one, create this one. And then if you are in the blue region in the composition range, which is going to have regular nucleation growth, you're going to get regular microstructure. So if I can create concentration modulation, either by additive manufacturing, diffusion annealing of multi-layer structures, whatever, then you're going to get this modulation of the microstructure. Then different location, you're going to involve different transformation mechanisms for the precipitation reaction. You're going to get different microstructures. So that's the hypothesis. And then so that's say we're going to expect this gradient microstructures, as we show here, by invoking the different mechanisms of the precipitation reaction. So let's take a look at the titanium alloys. We know this is regular nucleation growth. You have very coarse microstructure alpha beta, and then by involving this is pseudo-spinodal mechanisms, you can find it's much refined, and then you can find it's a super refined microstructure where you get involved the other mechanisms, congruent transformation or omega-assisted nucleation. This is all alloy composition dependent. So if we do have a concentration gradient, and we can create those microstructures. The proof of concept, we use phase field, and we have this free energy curves, And then we do the simulation. When we did find you can have all those microstructures within the same sample if you create this concentration modulation. Now, back to the critical question that we start. How do you create those concentration modulation, right? Okay, so you can create different ways for some of the systems in this particular system. And we have, so this is binary system. This is titanium vanadium. And we do have, in this case, we do have a spinodal decomposition. Let's see, you can get my cursor back. Yeah, so we have a spinodal decomposition in beta phase. And at this low temperature, this high temperature, the equilibrium two-phase mixture is going to be this one and this one. And the alpha phase is metastable. And then we take this two concentrations domains, and then we can quench to lower temperature. Then now the equilibrium phase is going to be beta plus alpha. And then you see this composition is very close to this crossover point. You're going to have, say, single phase beta. You can have very fine scale alpha plus beta. So you get this microstructure. So if you are familiar with titanium alloys, so that's the details of mechanisms for pseudo-spinodal. So I can skip that one. So you have, this is regular, we call it bimodal microstructure in titanium alloys. You have alpha HEP plus alpha plus beta. But you can, by this mechanisms, you can invert this bimodal microstructure into this one. And then, so in this case, you're going to have beta phase as the single phase. It's much more ductile, a lot of more slip systems, and then you have alpha plus beta two-phase microstructures. So this is one way to explore. But now we say, okay, let's take the simpler approach. We know we have this bimodal microstructure we see routinely in the titanium alloys. Why don't we simply take this microstructure, we do an upquench. We create what we call the ghost alpha. You dissolve the alpha structurally back to beta, but compositionally, they are still there. So this is called a ghost alpha. And this has been observed in the experiment. Then if you have the concentration modulation already at its fine scale, if you do the precipitation reaction, you get automatically this microstructure, right? You get it as a fine and then coarse alternating microstructure depending on the upquench experiment. So we take this idea, we did experiment this time. This is very easy to do, very easy to convince our experimental collaborator to do this simulation. You do see this is a very fine alpha plus beta, and then this is the original location of the globular alpha. You do upquench, you form the ghost alpha, and then you got this fine, and then you have a coarse microstructure in the original beta grains. And then if you check the properties, you do see that you have the enhancement of both the strength and ductility for two different heat treatment, different temperatures. So a very significant increase in the ductility of the material. All right, so let's try to see, summarize what I just told you. Idea is pretty simple: to create compositionally modulated material or structurally modulated material. If you do so at the right length scale, you can really confine the strain release because all the shear deformation, they share the same feature. Autocatalysis, long-range elastic interaction, strain avalanche. If you can find a way to confine those strain release, you can get the proper stress strain curve. So what I showed you, the first one, you can use concentration modulation at a nanometer scale created by all different means: laser, additive, and upquench dissolution, or spinodal decomposition, or deposition of multi-layers, and do annealing. So if you get those concentration modulations, it turns out to be very effective to confine the strain release during Martin-City transformations, which give you this linear superelastic, very low modulus, Inwa anomaly, and give you all those interesting properties. Then you can also utilize this is the concentration modulation can be produced by this laser based power back fusion process. I show you one example of those ones. You can create a very fine scale dual phase microstructure with a strong trip effect, give you the large uniform elongation. And I showed you the intrinsic coupling between deformation twin and Martin-City transformation. I call it extended twin boundary structure, which already have the DNA of Martensite in it. When you apply load, they are ready to go. So that's the other ones, which also give you linear superelastic behavior of the material. And the last one, we can utilize different transformation mechanisms depending on alloy composition. I can create a composition modulation by all the other means I mentioned early on. Then you can have a microstructurally precipitated microstructure modulated materials, which give you a kind of synergistic combination of the strength and ductility. All right. With that, I'd like to thank you very much for your attention. It's a very simple idea, and then just try to use the same idea again and again and try to get different properties. Thank you.